21 ECC 202T Analog and Linear Electronic Circuits Unit 2 Non-Ideal DC Characteristics and AC Characteristics of Op-Amp. Non-ideal DC characteristics of an op-amp. Although an ideal op-amp is assumed to have perfect characteristics, real or practical op-amps exhibit certain imperfections that can introduce errors in the output voltage. These non-ideal characteristics mainly affect the accuracy and stability of DC amplifier circuits. The important DC characteristics are input bias current, input offset current, input offset voltage, and thermal drift. These non-ideal DC characteristics must be considered while designing precision amplifier circuits, especially in applications requiring high accuracy and stability. Input bias current. The input stage of an operational amplifier is usually a differential amplifier made using transistors such as BJTs or FETs. These transistors must operate in their active or linear region for proper amplification. To maintain this operating condition, a small DC current is required at the input terminals. In ideal op-amp analysis, we assume that no current enters the input terminals. However, practical op-amps draw a very small input current called the input bias current. The currents entering the inverting and non-inverting terminals are represented by IB minus and IB plus. Due to slight internal mismatches between transistors, these two currents are not exactly equal. The average of these two currents is called the input bias current. So the input bias current IB is equal to IB plus IB minus divided by 2. Input bias current is an important parameter in precision amplifier circuits because it can introduce small output errors. The input bias current is calculated as the average of currents flowing into the inverting and non-inverting terminals. In bipolar op-amps, transistor-based currents are comparatively higher, resulting in bias currents typically in nanoampere range. The input bias currents for bipolar op-amp is usually around 500 nanoampere or lower. In FET input op-amps, the gate current is extremely small because FETs have very high input impedance. Therefore, FET op-amps have much lower bias currents, often in the picoampere range. At room temperature, the bias current for FET op-amp can be as low as 50 picoampere. Because of their very low input current, FET op-amps are preferred in high input impedance and precision measurement applications. To study the effect of input bias current, the input voltage is set to 0. Next, we are going to derive the expression for input bias current. Consider the circuit given in the right hand side of the slide. So, we are considering an inverting amplifier with bias current. Apply Kirchhoff's current law at node V2. So, I1 is equal to IB minus plus I2. Then we can write Vi minus V2 by R1 equal to IB minus plus V2 minus V0 by RF. The non-inverting terminal is grounded as shown in figure. So we can consider V2 also equal to virtually grounded. So by substituting these values, we can get the Vout is equal to IB minus into RF. Let's consider RF is equal to 1 mega ohm and IB minus equal to 500 nanoampere if we consider bipolar op-amp. So we can get Vout is equal to 1 mega ohm into 500 nanoampere, which is equal to 500 millivolt. Even when the input signal is absent, a small bias current flows into the op-amp input terminal and this constitute this output voltage of 500 millivolt. Such a large output error is undesirable in practical and precision amplifier circuits. Therefore, Methods such as offset compensation or the use of FET input op-amps are employed to reduce this error. The input bias current flowing through external resistors creates an unwanted output offset voltage. To reduce this effect, a compensating resistor called R-comp is connected between the non-inverting terminal and ground. The bias current flowing into the non-inverting terminal produces a small voltage across this resistor. Due to the virtual short concept in the op-amp, a similar voltage appears at the inverting terminal. The circuit is analyzed under the condition that the input voltage is 0. Applying KCL at the inverting node helps determine the relation between the currents and voltages. By choosing the appropriate value for compensating resistor, the output error caused by the bias current can be significantly reduced. This technique is commonly used in precision op-amp circuit to improve accuracy. By considering the circuit in the right hand side of the slide, which has a R-comp, we can get, using the Kirchhoff current law at node V2, we can get I1 plus I2 is equal to IB minus. Then by substituting the current expression Vi minus V2 by R1 plus V0 minus V2 by RF is equal to IB minus. But we have V2 is equal to minus IB plus into R-comp. Also, we have the Vi equal to 0 and Vout equal to 0. So by substituting these values in the equation, we can get IB plus R-comp by R1 plus IB plus R-comp by RF is equal to IB minus. Now assume both the input bias currents are approximately equal. So we can write it as IB plus equal to IB minus. Therefore, R-comp by R1 plus R-comp by RF is equal to 1. By solving, the compensating resistor gives R-comp is equal to R1 RF by R1 plus RF, or which is equal to R1 parallel RF. The compensating resistor technique used in the inverting amplifier can also be applied in the non-inverting amplifier configuration. The non-inverting amplifier configuration is shown in this slide. The purpose of compensating resistor is to balance the voltage drops produced by the input bias currents at both the terminals. So, if we apply the same concept here, we can get the R-comp as R1 RF by R1 plus RF, which is equal to R1 parallel RF. Next is input offset current. Bias current compensation is effective only when both input bias currents, namely IB plus and IB minus, are exactly equal. However, in practical op-amps, the internal transistors cannot be made perfectly identical due to manufacturing limitations. As a result, a small difference always exists between the two bias currents. This difference is known as the input offset current and is represented by IOS. IOS equal to IB plus minus IB minus. We consider only the magnitude of difference between IB plus and IB minus. The absolute value sign is used because we cannot predict which bias current will be larger. The typical offset current for VJT op-amp is around 200 nanoampere, whereas for the FET op-amp it is much smaller, approximately 10 picoamperes. Even if bias current compensation is applied, this offset current can still generate a small output voltage even when the input voltage is 0. Therefore, input offset current becomes an important factor in precision DC amplifier applications. Now let's derive the output voltage caused by the input offset current. From the circuit, the voltage at node V1 is equal to the voltage drop produced by the bias current through the compensation resistor. So V1 equal to IB plus into RCOM. Since the input voltage is 0, the voltage at node V2 becomes a negative of V1. So V2 equal to minus IB plus into RCOM. Next, by applying the Kirchhoff current law at node V2, the sum of the currents through R1 and RF is equal to the bias current IB minus VI minus V2 by R1 plus V0 minus V2 by RF equal to IB minus. Substituting the values for the VI equal to 0 and the value of V2, we obtain IB RComp by R1 plus V0 plus IB plus RComp by RF, which is equal to IB minus. After rearranging the equation, the output voltage expression becomes V0 by RF equal to IB minus IB plus RComp by RF minus IB plus RComp by R1. This shows that even with bias current compensation, the difference between the two bias currents still produces an output voltage. This unwanted output is due to the input offset current. Now let's simplify the derived equation for output voltage. Starting with the previous expression, V0 by RF is equal to IB minus IB plus RComp by RF minus IB plus RComp by R1. We note that the compensation resistor is equal to the parallel combination of R1 and RF. That is equal to R1 RF by R1 plus RF. Substituting this value in the equation and simplifying, we obtain Vout is equal to RF into IB minus IB plus. The difference between the two bias current is called input offset current. So IOS equal to magnitude of IB plus minus IB minus. Therefore, the final expression for the output voltage becomes Vout equal to RF into IOS. Now consider an example. If the feedback resistance is 1 mega ohm, the input offset current for the bipolar op-amp is 200 nanoamperes, then the output voltage becomes Vout equal to 1 mega ohm into 200 nanoampere, which is equal to 200 millivolt. This output error is quite larger and unacceptable for precision amplifier application. Although reducing the feedback resistance can minimize the offset voltage, keeping RF very small is often difficult in practical circuit designs. T-network feedback for reducing offset current. To minimize the effect of input offset current, a T-network feedback configuration can be used. This method is good practical solution because it provides a very large effective feedback resistance without actually using a physically large resistor value. As a result, the output error caused by input offset current can be significantly reduced. Using T to pi conversion, the equivalent feedback resistance is given by RF is equal to RT square plus 2 RT RS by RS. While designing the T network, the resistor RT should be chosen much smaller than half of the feedback resistance. RT should be very much lesser than RF by 2. After selecting RT, the resistor RS can be calculated using RS equal to RT by RF minus 2RT. Therefore, the T network is effective technique to obtain high feedback resistance while keeping the actual resistor values practical and minimizing offset current errors in the op-amp circuits. Let's see a problem on this. Design an inverting amplifier to obtain a gain of -20 and an input impedance of 5 mega ohm. Calculate the values of RF, RT and RS using T-network feedback circuit. So in the question, it is given that input impedance R1 is equal to 5 mega ohm. Calculate the feedback resistance RF. So for an inverting amplifier, ACL is given as minus RF by R1. ACL is given as -20. So RF is equal to minus ACL into R1, which is equal to 56 kilo ohm. Using T network formula, RS equal to RT square by RF minus 2RT. Rs equal to 56 kilo ohm divided by 100 mega ohm minus 2 into 56 kilo ohm. So Rs will be approximately equal to 31 ohm. Now let's discuss about input offset voltage. Even after applying bias current compensation and offset current compensation techniques, the output voltage of an op-amp may still not become exactly zero when the input voltage is zero. This happens because of unavoidable mismatches and internal imbalance in the op-amp circuitry. Therefore, a very small voltage must be externally applied between the input terminals in order to force the output voltage to become zero. This small voltage is known as input offset voltage, represented by VIOS. VIOS equal to voltage required at input to make V out equal to 0. In other words, input offset voltage is the differential DC voltage that must be applied between the two input terminals to nullify the output voltage. Since this voltage behaves like an unwanted input signal, it gets amplified by the op-amp and introduces errors in the output. Hence, input offset voltage is a very important parameter in high precision and DC amplifier applications. Let's consider input offset voltage for different circuits. So if we consider a non-inverting amplifier circuit, which is shown in the figure A. If Vi equal to 0 in figure A, it becomes like figure B. Now let's derive the expression for output voltage due to input offset voltage. By applying Kirchhoff's current law at node V2, I2 is equal to I1 plus I3. Since the op-amp input current is ideally 0, I3 will be equal to 0. Therefore, the current through the feedback resistor equal the current through the input resistor. Vout minus V2 by Rf equal to V2 by R1. After simplifying the equation, we obtain Vout equal to R1 plus Rf by R1 into V2. We know that input offset voltage is defined as the voltage difference between the two input terminals. VIOS is equal to magnitude of V1 minus V2. Since V1 equal to 0, VIOS equal to V2. Substituting this into the output equation, we get Vout equal to 1 plus Rf by R1 into VIOS. Finally, the input offset voltage can be written as VIOS equal to Vout by 1 plus Rf by R1. This equation shows that even a very small input offset voltage can produce a significant output voltage because of amplification by the op-amp gain. Next is total output offset voltage. In practical op-amps, the output is not exactly 0 even when the input voltage is 0. This unwanted output is called output offset voltage. The total offset at the output depends mainly on two factors. One is input offset voltage VIOS and input bias current IB. Without compensation, both these effects contribute to the output offset voltage. So, VOT equal to 1 plus Rf by R1 VIOS plus Rf into IB. When compensation resistor Rcomb is connected in the circuit, the total output offset voltage becomes VOT equal to 1 plus Rf by R1 into VIOS plus Rf into IOS. The first term in the equation represents the amplified effect of the input offset voltage, while the second term represents the effect of bias currents flowing through the feedback resistors. To reduce the error caused by the input bias current and compensation resistor R input bias current, a compensation resistor Rcomb is added. With proper compensation, the effect of input bias current is reduced and only the input offset current IOS contributes to the output offset. Since IOS is much smaller than IB, the overall offset voltage decreases. Modern op-amp often provides offset null pins. By connecting the potentiometer to these pins, the output offset voltage can be adjusted close to zero. Now let's look into a problem. For a non-inverting amplifier R1 equal to 2 kilo ohm, RF equal to 18 kilo ohm, calculate the maximum output offset voltage due to VIOS and IB, given that VIOS equal to 8 millivolt and IB is equal to 250 nanoampere, IOS equal to 40 nanoampere. B. The value of RComp required to reduce the effect of IB, and the maximum output offset voltage when RComp is connected in the circuit. So let's look into maximum output offset voltage without compensation. So the formula is VOT equal to 1 plus RF by R1 into VIOS plus RF into IB. By substituting the values which is given in the question, we can get VOT equal to 1 plus 18 by 2, 8 millivolt plus 18 kilo ohm into 250 nanoampere. So we can get VOT equal to 80 millivolt plus 4.5 millivolt, which is equal to 84.5 millivolt. Then for calculating the compensation resistors, we have the equation RComp equal to R1 parallel RF. By substituting the values, we can get RComp equal to 2 into 18 by 2 plus 18 kilo ohm, which is equal to 1.8 kilo ohm. Next, to find out the maximum output offset voltage with the compensation resistors, we use the formula VOT equal to 1 plus RF by R1 VIOS plus RF into IOS. By substituting the values, we can get it as VOT equal to 80.72 millivolt. Next non-ideal DC characteristics is thermal drift. In practical op-amp circuits, temperature changes affect important parameters such as bias current, and offset voltage. Even if the circuit is perfectly adjusted or nulled at room temperature, the output may shift when the temperature changes. This unwanted variation is called drift. For example, a circuit calibrated at 25 degrees Celsius may show a different output offset at 35 degrees Celsius. Manufacturers specify drift characteristics to indicate how sensitive the op-amp is to temperature changes. Offset current drift is measured in nanoamperes per degree Celsius and offset voltage drift is measured in millivolt per degree Celsius. Smaller drift values indicate better temperature stability. To minimize drift, proper PCB design is important. Heat sources such as power transistors or voltage regulators should be placed away from the op-amp. In high precision applications, cooling methods such as forced air cooling may be used to keep the temperature constant and improve circuit stability. Let's see a problem on the thermal drift. A non-inverting amplifier with a closed loop gain 80 is nulled at 20 degrees Celsius. Determine the changes in output voltage when the temperature rises to 45 degrees Celsius if offset voltage drift is 0.12 millivolt per degree Celsius. In this example, the temperature rises from 20 degrees Celsius to 45 degrees Celsius. So giving the temperature change delta T equal to 25 degrees Celsius. The offset voltage drift is given as 0.12 millivolt per degree Celsius. Therefore, the additional input offset voltage generated due to temperature rise is VOS equal to 0.12 into 25, which is equal to 3 millivolt. Since the amplifier gain is 80, This offset voltage is amplified at the output. Vout equal to Vos into ACL, which is equal to 3 into 80, which is equal to 240 millivolt. Thus the output voltage changes by 240 millivolt due to temperature drift. Next, let's look into the AC characteristics of an op-amp. The op-amp characteristics are generally divided into two categories, DC and AC characteristics. DC characteristics we have already seen, and next we are going to see the AC characteristics. The DC characteristics mainly affect the steady state accuracy of the amplifiers. The AC characteristics become important when the op-amp processes various signals such as sinusoidal or high frequency inputs. The two major AC characteristics are frequency response, which indicates how the gain of the op-amp changes with frequency. Gain decreases as frequency increases. Slew rate, it represents the maximum rate of change of output voltage with respect to time. It limits the ability of an op-amp to handle rapidly changing signals. For small amplitude sinusoidal signals, these AC characteristics determine the overall performance and fidelity of the amplifier. Frequency response. Frequency response explains how the gain of the op-amp changes when the input signal frequency changes. To study this behavior, we use a graph called frequency response curve, where gain is represented in decibel, that is dB, and frequency represented on the horizontal axis. In an ideal op-amp, the gain should remain constant at all frequencies. This means the op-amp would have infinite bandwidth. However, practical op-amps cannot maintain constant gain at high frequencies. As frequency increases, the gain starts decreasing gradually. This phenomenon is known as gain roll-off. The main reason for gain roll-off is the presence of internal capacitance within the op-amp circuit. These capacitance are produced due to the semiconductor devices used such as BJTs or FETs and the internal structure and layout of the op-amp. Because of these internal capacitive effects, practical op-amps behaves like low-pass amplifiers at higher frequencies. The frequency response of an op-amp is represented using magnitude and phase response curves. At very low frequencies, specifically when the operating frequency is very less, the gain magnitude remains approximately constant at 20 log AOL dB. At the frequency when f equal to f1, that is corner frequency, the gain decreases by 3 dB from the DC gain value of AOL. When here the frequency f1 is known as corner frequency or cutoff frequency. When the frequency increases very much higher than f1, the gain starts decreasing continuously. The gain decreases at a rate of minus 20 dB per decade or equivalently minus 6 dB per octave. The magnitude and phase curves are shown in the given figures. The practical op-amps are made up of several internal amplifier stages rather than single stage. Each stage contains parasitic capacitance due to transistor junctions and internal circuit layout. These capacitance combines with resistive components to form RC networks, which introduce poles in the frequency response. Because multiple stages exist, a practical op-amp has multiple break frequencies or corner frequencies. The overall gain of the op-amp is therefore affected by all these poles, resulting in multi-pole transfer function. The equation A equal to AOL by 1 plus J into F by F1 into 1 plus J into F1 F by F2 into 1 plus J into F by F3 is given for 3-pole op-amp circuits. Here AOL is the low frequency open loop gain. F1, F2, F3 are the break frequencies. J represent the imaginary operator. The transfer function in the S domain is given by A equal to AOL into omega 1, omega 2, omega 3 divided by S plus omega 1 into S plus omega 2 into S plus omega 3. The frequency response for this three-pole circuit is as shown in the figure. Stability of an op-amp. In open loop mode, an op-amp has extremely high gain, making it highly sensitive and difficult to control. Therefore, op-amps are usually operated with negative feedback to obtain stable and predictable performance. Feedback changes the gain and frequency response characteristics of the amplifier. The closed loop gain of the amplifier is expressed as ACL equal to A by 1 plus A beta, where A is the open loop gain, beta is the feedback factor. For stable operation, the denominator 1 plus A beta should never become 0. If 1 plus A beta equal to 0, the closed loop gain theoretically becomes infinite, causing continuous oscillations. This condition is known as instability condition or oscillation condition. Rearranging the equation gives minus A beta equal to 1. Two conditions must be satisfied for oscillation, that is, magnitude condition, magnitude of A beta must be 1, and phase condition, angle A beta equal to pi radian or 180. When these conditions occur simultaneously, then the negative feedback effectively becomes positive feedback, leading to sustained oscillations. In an inverting amplifier configuration, the op-amp already produces a phase shift of 180 degree at low frequencies. As frequency increases, the internal poles or corner frequencies of the op-amp introduces additional phase lag. Each pole can contribute a maximum phase shift of minus 90. Therefore, one pole up to minus 90, two poles up to 180, minus 180. When these additional phase shift combine with the original 180 inversion, the total phase shift can effectively become 360 or 0 degree. Under this condition, the negative feedback behaves like positive feedback. If the loop gain magnitude satisfies A beta equal to 1, the circuit begins to oscillate continuously. This phenomenon leads to instability in the amplifier. Instability means the output is no longer controlled and may grow excessively or sustain oscillations even without an input signal. Therefore, practical op-amp circuits are designed with proper frequency compensation techniques to maintain stability. Next important AC characteristics is slew rate. This determines how fast the output voltage can change. Mathematically, slew rate is the maximum slope of the output voltage waveform. Slew rate is equal to dV0 by dt. The unit of slew rate is volts per microseconds. Another related parameter is rise time, which measures how quickly the output reaches its final value after a step input is applied. In an ideal op-amp, the output should respond instantly to changes in the input signal. Therefore, the ideal slew rate would be infinite. However, practical op-amps cannot change output voltage instantaneously because of internal capacitance and current limitations. During large signal operation, if the input changes too rapidly, the output cannot keep up and becomes distorted. This limitation is called slew rate limiting. Slew rate is closely related to bandwidth. Wider bandwidth gives better high frequency response. That means higher slew rate. Practical op-amps have slew rates ranging from 0.1 volt per microsecond for general purpose op-amps up to 1000 volt per microsecond for high speed op-amps. Slew rate can be improved by increasing closed loop gain, supply voltage. Temperature increase reduces the slew rate due to changes in device characteristics. Causes of slew rate. To maintain stability and avoid unwanted oscillations, op-amp use compensation capacitors. These capacitors may be internally connected within the op-amp or externally connected in the circuit. The compensation capacitor slows down the response of the output voltage to sudden changes in the input signal. Since a capacitor cannot charge instantaneously, the output voltage changes gradually. The slew rate depends on how quickly the capacitor can charge or discharge. The mathematical relation is slew rate equal to dVc by dt, which is equal to I by C, where I is the maximum charging current available and C is the compensation capacitance. From this equation, large current result in faster charging and higher slew rate. Smaller capacitor also increases the slew rate. Therefore, high-speed op-amps are designed with higher internal charging currents and smaller compensation capacitors. However, reducing capacitance too much may reduce stability. So, a trade-off exists between the speed and stability. Next, we will see the slew rate equation. Consider a voltage follower circuit where the output directly follows the input signal. If the input is sinusoidal waveform Vn equal to Vm sin omega t, then the output is also the same waveform because the gain of the voltage follower is unity. To determine the slew rate requirements, we calculate the rate of change of the output voltage with respect to time. So by differentiating, the sine wave gives dV0 by dt equal to Vm omega cos omega t. The maximum rate of change occurs when cos omega t equal to 1. Therefore, the maximum slope of the output waveform is slew rate equal to Vm omega. Since angular frequency is related to frequency by omega equal to 2 pi f, the final expression of slew rate becomes slew rate equal to 2 pi f Vm. This equation shows slew rate increases with frequency. Slew rate also increases with signal amplitude. If the required slew rate exceeds the op-amp's rated slew rate, distortion called slew rate distortion occurs in the output waveform. The slew rate limits the highest frequency at which the op-amp can produce the sinusoidal signal without distortion. From the slew rate relation, for a sine wave, slew rate equal to 2 pi f Vm. We can rearrange the equation to find out the maximum frequency. So F max is given by SR, that is slew rate, by 2 pi Vm. Since slew rate is usually specified in volt per microsecond, we multiply by 10 raised to 6 to convert microseconds to seconds. Therefore, F max in hertz equal to slew rate by 6.28 Vm into 10 raised to 6. This equation indicates higher slew rate allows higher operating frequency, larger output amplitude, reduces the maximum usable frequency. If the input frequency exceeds F max, the op-amp output becomes distorted because the output cannot change fast enough. This distortion is called slew rate distortion and is common in high frequency, large amplitude applications. Now let's look into a problem on slew rate. A 741 op-amp is used as a non-inverting amplifier with a gain 40. The amplifier operates up to frequency 15 kHz. Determine the maximum peak-to-peak input signal that can be applied without causing slew rate distortions. Given slew rate equal to 0.5 volt per microsecond. Slew rate is given as 0.5 volt per microsecond and frequency is given as 15 kHz. So using the slew rate formula, slew rate equal to 2 pi f Vm into 10 to the power minus 6. Vm equal to slew rate by 2 pi f into 10 raised to minus 6. By substituting the values, we can get Vm is equal to 5.3 volt peak. Therefore, Vout peak to peak will be 2 Vm, that is equal to 10.6 volt. Then A is given as 40. A is the gain of the amplifier. So V in peak to peak equal to Vout peak to peak by gain. So V in peak to peak is given as 265 millivolt. Thank you.